Okay, so now we maybe have a little bit of intuition for the notion that equilibria are often not standalone systems. They're connected to other things that are happening in the system, and if you can affect one reaction that's connected to another, then you will change both of them. And we saw that with the relationship between solubility and pH, or acid-base reactions. So let's look at that now as it relates to complexation reactions, which are typically reactions with metals and Lewis acid-base systems. So when you have electrons, pairs that are then reacting with the metals in the system. So let's use the example that we've talked about before, which is the dissolution of silver chloride into its constituent ions in water has a KSP that's really small. So we say, ah, yeah, it's pretty sparingly soluble. So we can also write up this type of reaction, which is the silver ion. And silver ion actually really likes to react with ammonia. In this case, I'm explicitly indicating the lone pair here because this is a Lewis acid-base reaction where silver is the thing that's going to be accepting the electron pair. NH3 is donating, so we have a Lewis base and a Lewis acid. And we form what we call a complex. So ammonia is not charged, right? It's just taking those electron pair and it's donating them to silver, and it's doing that with two equivalents. So it doesn't change the charge on the ion, which means this whole complex is positive. We call these complexation reactions. This type of bond is what we call a coordinate bond, which you learn a lot about if you go on to take my inorganic chemistry class 275. Which is a whole other class of bonds where typically we think of a covalent bond as a shared electron pair where they each are bringing one electron to the party. In a coordinate bond, it's still a covalent bond, but now both of the electrons that form that bond come from one species. And so that's what we're getting here is this complex. So if this reaction can occur, what happens if we dump in some ammonia into a system where silver chloride is struggling to dissolve, right? At equilibrium in water, not much of it breaks apart, but then what if we toss in some of this stuff? So with a complexation reaction like this, we need to understand, well, what is its equilibrium? And to do that, we can look at each of the individual steps of adding ammonia. So if this is sort of the final reaction where we've added two equivalents ammonia, you can think about it as, well, it occurs one ammonia at a time. So we have the silver ion plus one ammonia that has some K. That K is around 2,000, right? So that means it's pretty heavily favored toward forming that complex. And then we add another ammonia to the original sort of mono ammonia complex, and we get the double. And so if we add these two reactions up, then we know that we can multiply the Ks, and those Ks then would correspond to this full reaction. So that looks something like this. We should be pretty familiar. This is no magic here. We're just adding these things up. We have an intermediate here. We cross that out. We get the same overall net reaction that we were targeting here. And we multiply K1 and K2 to get our new equilibrium constant. And I'm going to call this case of F for formation constant because it's an ion plus some Lewis base to form a complex. And so anytime you're forming or having things come together to form something, we're going to call that a formation constant. And again, you talk a lot more about this if you go on to an analytical chemistry course. But this is sort of meant as a preview to that and adding some nuance and flavor to the diversity of equilibrium reactions, and then using your intuition for Le Chatelier's principle to think about, okay, if these things are possible and they're occurring, how does that change something like the solubility equilibrium? And it's important to note that here our formation constant is pretty big, 10 to the 7th. That's 10 million. So it means that at equilibrium, we've got about 10 million times more of the complex than we do the products of the ion. Okay, so now we know both of these reactions occur. And so let's pretend that we want to understand what the impact of adding the ammonia is to this system. Well, we know that the second reaction occurs through this complexation, so we could add these two systems up to get a net overall reaction that's occurring in the system, and then evaluate what the overall K for the system is, and that could give us some idea of what's happening. Before we do that, though, let's just sort of use Le Chatelier's principle to see if we can predict what's happening. If you've got a beaker and that beaker contains just silver chloride, and that silver chloride is in equilibrium with its ions, you know that most of the species are going to be in the form of the actual salt. It's not going to dissolve, right? And let's then imagine you want to dump in just some ammonia, because you know that Lewis base can react with that silver ion and that it's got a quite huge formation constant, right? So if the formation constant is big, that means it's going to lie to the right for the second reaction, and it's going to quickly grab this and cause its concentration to plummet, right? Because it's grabbing it and converting it into the complex. And if the concentration of this species goes down, then the equilibrium of the silver chloride should push it in the direction of the ions to make more, because it still needs to satisfy this constant KSP. And so this is a really good example of using Le Chatelier's principle to rationalize what will happen to the system. So overall, our prediction may be that when we add ammonia to the system, we start to dissolve more of the solid, because we're chewing up a bunch of the silver, and this silver is the same, right? The silver in this reaction is literally the same silver in this reaction. They're not different. And so if we start to consume some of that silver and decrease it to make more of the complex, we are at the same time decreasing that same silver, which means that silver chloride needs to dissolve more to make more. That's the prediction using Le Chatelier's principle. So if we just add these things up, we're good at this, right? I can cross out the silver ions because it's the same on both sides. I get an expression that's our original silver chloride salt plus these two equivalents of Lewis base, makes the complex, but it dislodges that chloride ion, so that's hanging out there. And our Ks are just going to be the product of the original case. And so that gives us a value of 3.1 times 10 to the minus 3. So how is this useful to us? Well, we can take this K and then just compare it to our original KSP. So original KSP was 10 to the minus 10. Our new K, which has sort of been augmented by this complexation reaction, is 10 to the minus 3. So really what that means is that there's about 7 orders of magnitude more silver chloride that's going to dissolve once we add the ammonia to the system, because this is still the same silver chloride as we had in the absence of ammonia, and a very small amount of it dissolved. Here, the reaction, it's still not a huge K, but it's 7 orders of magnitude larger, 10 million times larger than what it was in the absence of ammonia. So just to be clear then, our K is much greater than KSP, so silver chloride is much more soluble when we have NH3. So if you physically added a chunk of silver chloride to a beaker of water, it would probably just sink to the bottom, and you'd end up with it sitting there because so little of it's soluble you wouldn't even notice those ions that went into solution. But then once you dump ammonia into the system, you'd start to see this disappear. It would actually dissolve before your eyes because you are increasing the solubility of silver chloride by about a factor of 10 million. So hopefully this is a good example for you to see the interconnectedness of equilibria and use some of the skills that we've already adopted in the past, like the ability to understand what a Lewis acid-based system looks like, understanding that there's a K for everything, and then understanding how Le Chatelier's principle is applied to other equilibria, and especially when you have equilibria that are coupled to each other in the system.